Okay.
Yeah, there we go. We're live.
All right. So welcome everybody.
Yeah.
And so I was just we tried to recall what we did a couple of weeks ago. And so our aim is to prove all of these theorems in this file about languages. So we have and last time we were trying to prove these theorems using Agda style and then tactic style. So we can see here, yes, nullable empty str.
Yeah.
So this is a theorem that says that the empty string is nullable.
Yeah.
And we proved it using tactics, and then we proved it using terms.
Yeah. Yeah. And now we need to do more of that, but we got stuck last time. And like the thing is, like with tactics, it does technically just generate code, which we could print, and we forgot how to print things. But Paul's figured it out.
Yes, I figured it out, but now I need to figure out what I figured out.
Okay, you forgot. Okay.
So,
he got the printout,
so if
but he forgot how he got.
Yeah, so I've got the printout. So these actually type check.
Okay.
Now there are a few things I wanted to discuss because, so for example, this t, if I just print it, so if I hash print t, oh, that does actually print something here.
Yeah. Let's try to copy that.
Yeah, I just want to get to the print. Maybe that was too simple, but basically what we were trying to print. So if I print nullable jar prime.
Oh, I see.
Yes. Yeah. So last time, what we did, now what we usually do with Coq is when we have something prove with tactics, we print out the term that it produced, and we just we can copy paste it into our code. However, if we do that here, it doesn't type check because it's not showing us all of the term. It's not showing us all of the term. So this thing here is the stuff that's missing. So this is not actually valid. It's hiding stuff. And so to see the whole term, you need to set an option. This one here, set option pp all true. And this is overkill maybe. But so if I do that and then call, then you get this thing.
Okay.
Right. So this actually worked. This actually type checks.
Okay, so this is what's pasted in on line 90.
No, so I paste, this is a subset because unfortunately I deleted what I had.
Okay.
But you can have a subset of these options. Whoops. Yeah, basically you want to choose a subset of these options to get something which type checks, but is not too big.
Smaller. Yeah.
However, the issue is that this really doesn't help understand what's happening anyway.
Well, I guess if you start simplifying it manually, right? Like a lot of this can be like universes that could have been inferred and that don't necessarily need to be there.
So I was trying to do it. That's why I was doing here. I tried to do it with simpler, like how you meant to use this false elimination. So that's why I've got this one here to try and get something simpler. And in this case, you get this no confusion is important.
Yeah.
But what I was confused by with no confusion is
I think
every inductive. yeah, every inductive type has a no confusion.
Hmm.
So if I print nat.no confusion. Oh, well, yeah.
Maybe now don't say it all to true.
Yeah.
Yeah.
Oh dear. Well, I've unstashed it, so I'm going to overwrite now.
Yeah.
Right. So we have.
Hmm.
I'm going to move your faces. That's more than I was expecting to see. So maybe the set has not registered itself on.
It's less than it was before. So
Yeah. So maybe if we just look at the type. So you have V1 and V2, which are natural numbers.
Oh, yeah, you can do
and V1
check.
equals V2.
You can do
yeah,
check instead of print if that's.
Yeah, that's what I'm looking for.
Yeah.
Yeah. So we're just interested in the type. Yes.
So if you have
no confusion.
2 natural numbers,
yes,
and know that they're
equality
equal,
between them, you get this no confusion type.
Okay.
And then no confusion type.
I guess now you need to print, maybe.
Yeah, now I need to print.
I read something about this before, but I forgot. But this is not very helpful.
No.
But yeah, we only need this. We need to understand no confusion to understand contradiction. Just to
exactly. So it's yes. So it's a way of expressing the fact that. So basically, what we have here, we're expressing an equality of two things which are constructed differently. And then somehow the no confusion types allows you to say, well, it's like it allows you to say, well, if two terms are constructed in different ways, then they're not equal. Something like this. And so what I thought is that maybe we need some, if we want to write these terms out, we need some kind of equivalent no confusion for our equality. So this this check no confusion. Oops. This is involves V1 equals V2, so the normal equality. Yeah. Maybe we need some equivalent thing for
type.
This type equality, or whatever we call this thing.
Well, this is no confusion operates over sort, which means it also operates over type. Like sort operates over prop and type. And I think since it's generated for each inductive type, it has to be generated over sort to be general enough. So I think it's fine. Like I don't know if we can do better. Because also generate for nats and lists and
So what's the cases on? So that
cases on is also generated for
generated
each type, right?
Yeah.
So much generated code.
Yeah. So this is like part of the induction, but you get to say, yeah, what is this saying?
Yeah, I'm reading, sorry, I'm so silent. It's just, yeah, this looks a lot like the definition we have, right?
Yeah.
If you look at TEQ in the type file.
REFL.
Yeah. If you print it here, then you can see both at the same time, and then
I'll print.
If you print it on while you're in that file, or do the check while you're in the file, then we can see both at the same time. You'll see it's like very similar.
DQ.
With dot cases on. Yeah, and then just make it a little bigger.
But isn't that what I?
Yeah, I just want to see both at the same time. Like the text is large enough, just the right side. Just so that it's, and then go to type.lean. I want type.lean open and the info view open. Yeah.
I mean, because I've printed the type cases on here.
Yeah, that's exactly what I want. But so I want lean type.lean open on the left.
Yeah.
And then the info view on the right, and then we can see the inductive type, and we can see cases on printed at the same time, right? And yeah, so this is all I wanted. Like, and now you can see how cases on is very similar to the inductive type. It's a very like small change, but it allows you to just do cases by providing like you provide the motive function and then a function that is based on the motive. So you're just doing like induction basically, but just not induction, the simpler version. So you'll see like you have two parameters you have to pass in here, like the rest is all fluff. Like three. Okay. The one is the motive, which sometimes can be inferred.
Yeah.
The other one is the actual type you want to do cases on. And then you have the function that will run on each case, or the case that it is. And so that function is dependent on the motive function. So you pass like the function type is dependent on the motive function. So it looks weird, but it's just a normal. Here's a type and here's a function that can operate on the cases. And this is the ReProving case function. And so if we now go back to like calculus.lean, and now we can see what's actually been done there, right? So the motive could maybe have been inferred, but like we're returning false, so probably not. And then we have A, which is the type we're going to do cases on. And then we have the function that operates on ReProving. So, because that's the only case, right? So that takes our age, and then it needs to return false, but yeah. And no confusion is a function that needs to take two numbers that are equal to each other. So that's the EQ riffle 2 that comes in there.
I see. Yes.
Yeah, but yeah, it's not
and then you end up with false, and then you can
yeah, I'm not
do
sure.
a limb on it.
Yeah, so how does Agda do contradiction again?
I think it just knows that it that this is not inhabited. I think that was the point. So if we try and do, maybe if we try and write this in Agda, then we can see.
Yeah,
Yeah,
you'll have the empty pattern, and then you don't need to provide the body, and it will infer that automatically.
okay, can we see?
Yeah.
Yeah, so how do I, so I do like, this, let's go and define a function.
Yeah, what does a function look like?
Single, oops.
Yeah.
One. No.
Yeah.
1 equal 2. 2. Is it called false?
Well, in the standard library, I think it's bottom,
called,
but
Cool.
like /bot, but
Right.
I'm not 100% sure. I could be wrong.
I think that's right. That's right.
so then say F question mark something. No. So I don't know what I'm writing, if that's correct or not.
No, that's yeah, it's a question
I
mark.
want to just put a hole in here.
Should you put this inside the code?
Where is the code? I thought this, I mean, a
Oh,
literal
you have to
act.
say, you have to say
Oh, it
begin.
needs to be in one of these things. Oh, yes. Okay. Fine. Parse error. All right. So it's not happy because can't do that. Maybe.
Maybe go up.
Now it's happy.
Out of the.
Maybe I'll put it down here.
Okay.
Oh, let's go. F type 1. Okay. Agda. Okay. Oh. Did I need to put curlies around here?
Yes.
And then I need to write some
So you
case.
You need to load again.
Oh yeah. Then I say case X.
Yeah.
This type check. Okay. So this just means there's no, it knows there's no inhabitants of this. Oh.
Right? What? How does it know that?
So
I guess this is the injectivity of the constructors.
Whoa, that's
yeah, I think the cases just splits up the variable into all possible constructors, and well, there's REFL is the constructor, but REFL doesn't make sense here, so there's nothing left, essentially.
That's
So for the REFL to be pattern match, then it needs to match successor of 0 to successor of 0, right? So then, okay, the first successor is fine, but then you need to match successor with 0. And because, as Paul said, injectivity of constructors, that doesn't match. So it finds the empty pattern.
So I think that no confusion thing is the equivalent of this injectivity of constructors in Lean 4. It's an extra axiom you get from an inductive type. But it's not as straightforward as this.
Yeah, that is.
So if you want to, that's why I didn't have time to investigate, but I think if you want to write terms, then we want to like have some no confusion type thing for our special equality, which is works. So we want to say like the injectivity property that applies for normal equality is also true for our equality. Because at the moment, like we need to it needs to be delegated to like the normal equalities check. So you have to, that's why you have all this list.no or nat.no confusion.
Okay.
So
okay.
I think if we wanted these to be shorter, we'd need to have like equivalent helpers for stuff that looks like this no confusion thing.
Check the t-decidable.lean file. Maybe we get lucky, maybe. And then just search for no confusion in here. Inside the file.
Yeah.
Or just confusion. Maybe confusion is enough.
Confusion.
Okay, no. Okay, I didn't do anything. Okay.
Yeah, so that was my that was my conclusion anyway, that when we look at this nat.no confusion, we'd like to have a version of this where instead of wherever this is, why is it? Oh, I need to print it. Check. Yeah, so instead of the normal equality here, we could have our equality instead. Then I think it would make some of these term proofs shorter. Because basically we want to be able to assert injectivity with our equality rather than have to delegate it to the normal equality.
Okay.
But this is,
I think you're right.
I didn't get around to looking at it apart from that. Was my conclusion from that.
All right. I think you're right.
So.
I will take that on offline because I think it's. I don't think it's going to be fun to.
No, we shouldn't do it now. That's. I mean, the conclusion for us is that we're not. That it's not. Well.
Yeah, we need some more.
I was going to say that. I was just about to say it doesn't seem viable to write the term proofs for these.
For the contradiction ones.
Yeah, for the contradiction ones. But I actually didn't test that. Like, if we clean this up, for example, how bad would it look? But I thought it looked bad, and then Then my conclusion was it looks bad because of this problem here, that the fact that we have this injectivity is on the wrong equality. But
yeah,
could be wrong.
I think you're on, at least onto something.
Yeah,
I'll try to figure something out. So let's for those proofs for now, let's just use contradiction. like the contradiction tactic in those cases, and I'll try to figure out like, oh, we're just missing this thing for type because we're not using prop, and it is actually fine. Or maybe, cool, I find out we're totally on the wrong path. Everyone always has to use no confusion, and then I can report that back too. But yeah,
basically we need a Zulip post with this question.
Yeah, but let's not
suitably tailored down to the
Let's do proofs as far as we can in Agda versus tactic style, but just always use contradiction where we can, and I'll clean it up, or I'll try to find out what can be done and explain it in a future stream. But yeah, this was a good find.
Okay. So we got. That's basically what we were doing last time.
Yeah. And we can continue with the other proofs.
Yes. So here we have
contradiction.
Continue with concat.
Like this one. Yeah, this will be hard.
Is this a contradiction one?
No. No, it's just ReFl and constructors. It's and even if it is, it's fine. Like you can always go start in Agda style and just write by contradiction somewhere and continue. So yeah, like
okay.
Yeah. So we've done. Are we sure we did all the easy ones? Are we really at concat
Nullable
already?
star.
Oh no.
Derivative empty strip.
Oh, but let's do this. This looks good. Like this sort of just something.
I mean, in Agda, look at it. It's just but this is. These look like These look like asserting uninhabited.
Oh, I see. Yeah. Okay, that is what it is.
So when we see that, we want to skip it. I don't know.
For now. Yeah.
For now.
This looks the scalar one. Oh, this derivative char. This looks good.
Yeah.
Yeah, so something I still need to do, just to be clear, is like in this case we just have an equality where we're actually supposed to have like a that
isomorphism.
That thing. And it has, well, as defined in the paper, it requires 4 proofs. So 2 extra for inversion that is not currently required by my definition, so I'll still need to add that later, but we can prove the first 2.
So we're saying the derivative of A at a char C is equal to this magical thing.
Yeah.
I don't remember. Right, so it's
saying you have some language P, and so language takes a word, right? So that's why we're returning a function that takes a word. But S is just some type. So we're returning a language which takes a word and returns a product of whatever this type is and the language with the word passed to it. And so it's like a easy way, like if we go back to the proof we're going to do, I think it will be a good example to explain it. So this says like if A is equal to C, right? So just in general, like if you don't look at any of this, just derivative rules. If you take the derivative of some character C with respect to A, you return the empty string if they're equal, and if they're not equal, you return the empty set, right? The empty set in this case is empty, it's false, it's it's yeah, nothing. It's the absurd type. And the empty string in this case is unit or true. So what we're saying by multiplying is we're getting rid of any if else here. Because we're just saying if A is equal to C, we have like we have a type. And if it's not equal, we don't. So the sum product of a no type is not a type. So it's effectively the same as false or absurd or empty. But if they are equal, then we do have a type. It's ReFL. So we're all fine. And it's effectively the same as just the empty string or unit or true. Does that make sense? Or did I just waffle?
Well, I'm not sure. It's been a long day.
Okay. Okay, how about
hoping that some of our proof automation will take some of the thinking away.
yeah, no, totally. I can I think I can also quickly share a screen and explain.
Yeah, that would be great.
Because yeah, I think I need to type.
Yeah,
it's not.
That's another homophone of type. So we have type, and type.
Yes.
Or however you do it in Afrikaans accent.
Keep tuck.
Tuck. Okay. It's more sensible language. You've got to distinguish between those things. Type and
just
type.
some of them. Just some of them. Okay, I'm sharing. Is that okay?
Yeah.
Okay, and it's switched over, I hope. Yeah, cool. Okay, so we want our calculus. Yeah, we are there. Okay. Okay, so we have this thing.
Mm-hmm.
So what, right? What if this is what is this, right?
This is uninhabited.
This is uninhabited, right? So this is kind of false.
Mm-hmm. Yeah.
This is just kind of true, right?
Yep.
It's a kind of true. And so now if I say scalar, right, it's something that takes a word
Mm-hmm.
and returns whatever this is, right? So false, say for example, and because it's just a product is just a tuple, so it's going to be false and the empty, right? This is one scenario. This is one scenario. And the other one is that we end up with this, right? Now, and this depends, like if C can be A and A can be A or B, right? That's kind of the only scenarios that matter. There's obviously more chars in languages. So, and just a reminder, a language is something that takes a word and just returns type, right? So let's just double check that I'm not talking shit. So yeah.
Yes.
Language takes a type, Oh, it takes a list, so a W, and returns a type. Okay. And the empty string is a language which returns if that type equals the empty list. Right, so we can put that here. So okay. And yeah, so this is, so the derivative of this will either return this or this, right? This is if they're equal, not equal. And this is if they're equal. Okay, what you want in the real world, just if you're just implementing this, right, is just to say, if they're not equal, right, then the derivative is the empty set. And if they are equal, then the derivative is the empty string. Okay, so actually, let's take this back. I think this was better. Okay. So you just want to return, in this case, and in this case, you want to return the empty string, which is just going to be that. You don't even care what W is. So, well, actually, you wanted to return this. Okay. So we can see, like, okay, this should also be P empty because we're use different types here. But okay, so what is the product of P unit and EW? Like in terms of like algebraic data types, this is one.
Well, it's isomorphic to empty string W, right? Because it's just, you can only have one thing in the left-hand component.
And it's the same as this.
Right. Yes.
And this, you can't construct it.
Yeah, you can't. Yes, you can't inhabit it with anything. So,
so it's the same as this, right?
I see.
And so you end up with this. So in both cases, they're the same. But if I wanted to write this, I would need an if. I would need some type of if expression that says if they're equal, then return this. If they're not equal, then return this. But if I can make the if go away just by using a scalar, like just by multiplying with 1 or 0. And this thing allows me to get 1 or 0, which means it just goes away, gone. So yeah, it's just a syntactic
Interesting trick.
Yeah, it's a nice trick. So yeah, there's various versions of Brzezowski, but like this is they don't use scalar, but they use concat instead of scalar, and then they can and they ask the nullable function to, instead of returning true or false, return a regular expression that is the empty string or the empty set. And then you say concat this thing with whatever the result was of the nullable function and the next thing, and then you've also gotten rid of an if. Because if you concat something with the empty string, that's the same as just returning the right-hand side. And if you concat something with the empty set, that's the same as returning the empty set. So yeah, it's This trick I've not seen before, but it is in the same spirit of the concat trick. Yeah. I will. Does that make this make sense now?
Yes.
Gregor?
I think so. I'm still trying to figure out whether there's a simpler whether there's any way to reproduce this this empty pattern in lean. Wasn't there something like the absurd pattern? Doesn't that work? The absurd type, doesn't that work somehow similar to that empty pattern?
What do you? Are we back to no confusion?
No. The reason I'm saying that is because of the PMD case where you said we cannot construct that type.
Yeah.
So in Agda we could do that with the empty pattern as well, right?
Yeah. There's So this is PMT is just for it is empty. It is the empty type, but it allows you to specify the universe as well, where empty and lean does not allow you to specify the universe for some reason. So it's just a more general version of empty, and it's the same as false for prop in the prop universe.
Oh, okay, I see.
Yeah, so it's just an inductive type without any constructors. That's
Oh,
it.
okay. So we don't even run into any problems of not being able to construct the second half of that pair.
Yeah, that's exactly what we want. We don't want to be able to construct it. So
Yes. Oh, okay. No, I think then it makes sense.
okay. Yeah, because that's the only way it can be zero, right? It's it is false. It is empty. We cannot construct it, so this type cannot exist.
Yes.
So it's effectively false. And that's exactly what we want. When you're taking the derivative of a character and with respect to another character and they're not equal, then, well, not supposed to get anywhere. You're supposed to say,
That makes
well,
sense.
we tried. This regular
Tried my
expression does
best.
not max. Like, if you add an or there, right, then again, things open up, right? But that side is squashed, like it's gone. Yeah.
Oh, okay, yeah, then it makes sense, I think. For me.
Cool. I'm gonna hand back to Paul's screens. Yeah. If I can find out how.
I think I could just hijack your
Please hijack.
share.
Excellent.
Then we'll see how much we understand from.
Yeah. So now let's just use some tactics and play. Right.
Okay.
Just to start off with, and then we can do the Agda.
Let me get rid of all this.
No.
I've got some. What? No, I don't. I just mean I want to get rid of these prints.
Oh yeah, good.
Because they're clogging everything up.
Yeah.
Well, there's only one of them, but
yeah, you can turn off all messages. That helps. Like you just collapse all messages on the right.
Ah, that's what I wanted. Thank you.
Yeah.
And where were we?
The one without sorry or to do. Yeah, there we go.
There we go.
Okay.
So we have one goal.
So we can do. Have we done intros here?
No.
Maybe give them names.
Yeah.
We're not in cock anymore.
Yeah. Okay, so we've got
maybe sump.
yeah. See what simp is doing.
Oh,
Made no progress.
Hmm.
So maybe we're missing some simp rules here.
Unfold the derivative one.
Yeah.
Oh, no. No, no.
Okay, so now we got function. Um,
I think.
what is the meaning of this then? C.
Yeah, C is just a character.
And then
Well, no. C is a language.
a language.
That is a character. C.
Yes. So we want to. You want to unfold that?
Sorry?
Can we unfold that? Because we want. Presumably this.
Yeah, we
is
can.
Function, isn't it? So.
Unfold char.
Yeah. There we go. Then we have you got anything in the listening?
Well, by the way, what does Rifle do just before?
Right.
RFL. Okay, sorry. Okay,
Yeah,
so you can unfold char, unfold the empty string.
Yeah. Oh, sorry.
Yeah, I don't think it's notation. So, I think empty stir, maybe?
Yeah. Exactly.
Okay, so the equal sign, right?
Yeah.
Is an implication, right? If I remember correctly. So or is it just? Oh no, it's just
this one here.
Oh, it's just Rifle. Yeah, that one. I feel like I want to do intro W, but I think it will.
No, because this is on the left of yeah, because this is not. There's nothing to intro here, is there? Yeah, because it's like we're inside of that triple equality now. So we've only got an A and a C, and then we got on the left-hand side we have a function, and on the right-hand side we have another equality. So it seems like the on the right-hand side we should end up with a function. But how? We got this.
What's the precedence of the implication and the equality? Is it a function returning an equality, or is it a function equal to something?
So this is the left. This is the left-hand side of the middle equality here. So we have this equality, and because you can hover over to see the precedence.
Okay.
This function's on the left,
and
this is on the right.
The function returns an equality. I see. Yeah. Okay.
Well, then the types match on the left and right because this is a function and this is a equality.
Wow.
So that makes sense to me now.
What is this dot after the C?
Yeah, so we should unfold that maybe.
Okay.
This is the whatever language.
That's a
What
good.
is
That's scalar.
Oh, it's scale. That's scalar. So if we unfold scalar, we might have some.
That's a good idea.
Okay, so now at least we have two. We have a function on the left and function on the right now, which is good.
So
we can do
I guess we need function extensionality, or how are we supposed to prove this?
Yeah.
I would like what one thing we can do
Well,
is
the thing
just,
is, yeah.
like very lame, but just do cases on A and C, and then you get all the cases where they're equal and not equal, but it's
Yeah, because this is this is only true if W is empty and A is equal to C.
yeah.
So this thing. So if W is equal to empty, or if W is not equal to empty, then you just have to check that the right-hand side is also uninhabited. So yeah.
Well, yeah, I would do it on like A and C and not on W.
Oh yeah.
But
I can't remember the syntax. I'm sorry.
Yeah, we have to do one at a time. I think this case is a with space with, and then
Then the type. Yeah.
and then
Yeah, but what can I?
some A tick. This A is a char, right? And then implication with a double.
Yeah.
And then sorry.
Make sure I got it right. It's not A is not an inductive type.
Okay, great.
Which is true. Yeah.
Oh, it's alpha. Oh, great. Yeah. Okay. So what function extensionality? Like, what did Jan say? Like,
yeah. So function extensionality, I think, says that if two functions have the same outputs for all inputs, then you can say that they're the same. But this is you need an extra axiom for that. So maybe there is for next something.
yeah, there's fun
complaining.
X.
What?
Yeah, it's the thing.
Why is that not complaining? What did it do? Did I apply it or something? No.
What happens if you go to the next line? Is it proven or?
No.
Tab in? No. Okay.
What is this? Oh, so it's just going to do nothing if it tries apply function extensionality, introduce new hypotheses, keep applying for next lemma until the goal target is not usable to.
Oh, because it's this function extensionality for the linear equality.
Oh, look, yes, this is another. So we need function extensionality for our equality. Similarly to no confusion.
Well, is it true?
What fun.
It doesn't.
We might just need to backtrack.
Well, just go back. Sorry to the.
Yeah.
Yeah, okay, and scroll down a bit. No, okay.
This has
Scroll
gone
up a
down to
bit?
something else now. Yeah.
No, okay.
So this is the
So I'm wondering if this is implemented in Lean or like.
next tactic.
Because I think funx is just a function. Like if you can do check funx.
Yeah, that's why I was trying to click here, but it's not taking me anywhere.
Oh, okay.
But presumably it is it's applying funnext, so that must be a function, not a tactic.
What if you do
So
check funnext in a file?
Let's do that. I probably need to import some.
There we go.
Yeah, so here it's saying like
Oh, there's a normal equality there.
f of g, then for all x, f of x equals g of x, then you say that f equals g. But this is the normal equality.
Oh,
Yeah, here's the problem. We need a whole infrastructure for TEEC.
this is pretty deep. Oh.
Hopefully we can derive it from a normal equality or something. I don't know. But yeah, this is not.
I think functional extensionality is something that is implemented pretty deep in Lean.
Well, it must be an axiom, right? Because you can't derive it. It's not.
Yeah, it's something that you can turn on and
true
off as well.
Yeah.
Oh, but if it's an axiom.
Yeah, it's off. Oh, hold on.
Hold on.
Hold on. It's often an axiom-independent type systems. And it cannot be proved from the core logic alone. In Lean's types theory, this follows from the existence of quotient types. Ah, okay. So it's a theorem in Lean's type theory. Like in Koch, it's not a theorem, it's an axiom.
Wow, okay.
But Quat must be involved the normal equality, right? Well, this thing is so that's the part that goes deep in the theory.
Yeah, and that looks like normal equality up there.
Yes.
But this sounds like it's safe to introduce as an axiom.
In Agda, it's also used as an axiom. Yeah.
And just something to note, a big difference between Agda and Lean.
However, if you look at the Koch proof, it doesn't use function extensionality. Sorry, the Agda proof doesn't use function extensionality. Well, as far as I can see, anyway. But maybe it does.
No, it doesn't.
Okay.
Yeah, so so we don't need it.
Okay, let's try to prove it in Agda.
Yeah, let's try and prove it in Agda. Maybe about Siri. Okay, so let me find this in Agda. Let's get rid of this before it causes us problems. No. I'm going to search for you. Oh, I want to search for this. Sorry. And then I want to search for this again in this file.
Yeah.
Yes, here we go.
Cool.
Right, so if I just start with this, comment this out. And so I know that I have to write this because that's my, then what do I do? Do refine? Yes. I want to Agda next goal. Yeah. Right, so let's look at the type of this because it, for us, it only applies, right, because like you were saying, Walter, that actually not all of this applies to us because it's the final two. So what do we actually prove? Just this one. And this one. There's no equality here at all, which may help.
That's my mistake.
Maybe that's why. That's why. No. Yeah, I'm just saying that maybe if there was equality here, we'd have more of a problem in Agda even, precisely because yeah, isomorphism may be easier to describe than equalities.
I'm sorry, that was my mistake.
No, we just discovered why it's an isomorphism rather than an equality.
Okay,
but isn't Agda using propositional equality as the inverse, like as the
okay, we can look at the inverse
equivalence relation in inverse.
Ah, good point.
Yeah.
Yes, we can see it down here. I think.
Yes. So I think Agda uses propositional equality as well.
So this is saying that G and F are left inverse, and then the other one is saying that G and F are right inverse.
Yeah, but what
that's
is
different from saying?
What is the tilde equal to?
Yeah, let's have a look.
I think it's up here, or no, I don't know. Yeah.
Yeah, so I think this is we ended up here last time, I think. So this is like parameterized over equality, but if we look, you see down here where it says function inverse L, then we've got these arguments.
I don't know, like I feel like this inverse just needs me to prove tilde equal to. And that seems to be a relation, which I don't know what a relation. Is that prop for Agda?
So you can replace the way v equal _2 by propositional equality here.
And propositional equality, that's like Agda's prop.
No. That's the only equality defined in Agda, and that is in type.
In type.
This is the triple equals.
Yeah, so in Agda, you never use prop. You're always in type. That's what my understanding is, and that's what Connell told us when he joined.
Okay, so thing. Okay, I'm sorry, it's taking me a while here.
No, so I think
so what?
So we have here we are. So we have like equals Kong here. So this is telling us what we need to provide for this MK if and only if. And we have the triple equals here.
Okay.
But this is different from the function extensionality because we have to prove that they're inverse. So we don't have to prove anything for. We don't have to prove that the functions are equal. We just have to prove this proposition.
Yeah. Which looks very similar.
Yeah,
But
it means you don't have to use function extensionality.
Okay, but maybe we can define this in lean. Like now, that would be quite like maybe with a 5-minute break, but and then we can
that would be good.
Cool.
See you in 5 minutes.
Yeah.
I will not join back today. I'm exhausted.
Yeah.
I'm very
Fair
sorry
enough.
for that.
No, thank you so
No
much.
problem. Thanks, Jan.
Okay, see you next day.
Cool.
See you.
this is kind of breaking my brain, but I think, we figured out my mistake.
Yeah,
So
gladly.
yeah, if we just redefine, if we just define the double implication properly in Lean, then we don't have to make this mistake again. I say we, but I mean I. It's just me.
Yeah, this difference in how equality is handled seems to be like seems to cause much more problems than I expected.
Yeah, no, it's a fundamental thing. So I was quite worried, but learning a lot, so it's not no deal breakers yet.
Not yet. How is that double implication defined, though?
So it's something Connell defined as far as I can see. So it's basically it's a normal double implication, but then it's also, so you have x implies y, y implies x, but then you also have x for all a, x of y of a, no, yeah, x of y of a is a. So you have this inverse, and then you just also define the inverse the other way. So you
Okay.
have to, so this implications, instead of only taking 2 proofs, takes 4 proofs.
Yeah.
So that's
This is what you're talking about here. So you define
yeah.
this if and only if, propositional if and only if. You need to provide the function that goes one way, the function that goes the other, and a proof that f and f minus 1 are left inverse, and a proof that they're right inverse.
Okay, and let's just correct what I said before here. This is not something Connell defined, as we can see now. Like, this is just in Agda's standard library. So yeah.
Okay. I haven't come across it yet.
Oh yeah, it is, isn't it? Sorry, yeah, I hadn't noticed we were out. We've gone to the standard library. But maybe Lean, no, I was going to say maybe Lean has it, but it won't, because we need to use our equality. Okay, so we're abandoning this for the moment.
Yeah, we'll keep it file open.
Yeah. So where should I put this?
I think tipper is good
instead.
for it.
Oh, tipper. Okay, let's put it again.
Type.
So we have this here already, but that's type if and only if. Then we need like prop if and only if.
What do you mean prop?
What am I talking about?
Yeah,
I meant type isomorphism.
Is that what it is?
I think and we can also refer to the paper because I think it gives it a name. I think I would call it an isomorphism, but
cool.
Let's see. So this long thing, right?
Yeah.
Here we go. Extensional isomorphism. So we've got type isomorphism, extensional isomorphism.
No. This. Yeah.
And extensional means pointwise.
Okay.
Oh no, this is not the right one. This is like extensional functional extension.
Yeah, we need both. We need both anyway.
Type isomorphism. So we should call it type isomorphism.
Okay. I like it.
Okay.
So TISO.
TISO. Yeah.
TISO.
And then we need alpha and a beta.
Yeah, but I think we can use a like tuff above, like copy and paste stuff and then start editing it.
Oh, it's a structure. Yes, yes, yes.
Hmm.
Yeah. So I will need that as well. So this is a ISO.
Yeah.
But we need a AB type.
I was
So we
thinking
have
ISO with an I,
yeah, why not?
because then it also does the ISO part. This.
I see.
Yeah.
I'm with you.
And then small s, just to be like super pedantic.
Yeah, otherwise it looks like we're deranged, right? This is
Yes. Yes. Thank you.
So we'd have this is like F and is it really modus ponens? But then we need
more.
I'm confused about this notation. So intro is what does this mean?
Intro is the constructor name. We'll only have one, so
yeah, and this is the type. Yeah,
we'll have many fields.
Yeah, I'm really confused about what this notation is. So
okay, so it's just like we're gonna have many fields, right? It's a structure with many fields.
Yes.
And so just think of line 76 as 67 as defining one field. And
so what does this mean?
Another field.
Intro.
That's just a constructor name, because we're just going to have one constructor, but many fields for that one constructor.
I see.
There's no other way
so
to
we
construct.
have, yeah. So
actually, let's go back to the Agda just for a second, I think.
Yeah.
To the, yeah, there we go. Okay, so
we've got F and F inverse, and then we want, I think we can just do this one here. So we want proof that for all X, NP composed with NPR, X equals X. That's the proof that we want. We want
so we don't want modus ponens, right?
Well, we need an F and an F inverse.
Yes.
This is F inverse.
Tick.
I don't know. I'm going to call it this maybe.
Okay.
Or you want to call it F tick.
Yeah.
Then we have another field which is F inverse. Well.
Yeah.
Then this is for all X.
Okay.
What do I put a card?
Yeah.
Then I do F prime X.
Yeah.
Don't need the parens, and then equals X.
Equal. Yeah.
Yeah. Maybe like left. I don't. Well, we need to give this a different name, but I'm not sure.
F.
Yeah.
I mean, yeah. Totally happy to bite shit on these names, but
yeah.
let's just get something.
So this is it, I think.
Yeah.
So I think we need to comment this or whatever. But
yeah. Fuck that. Just take the comments away. That's Walter's problem.
And then we need a longer thing here.
Yeah. Yeah, we can just remove line 60. Just hopefully.
Remove line 60?
Yeah.
We're not going to use this Unicode thing.
Yeah. Hopefully.
But you You want to get rid of this?
Okay, I'll do that later. Don't worry. Okay.
Oh, I could just delete it. So big thing is we can have long Unicode arrow.
Yes, we could.
Yeah, I don't sense enthusiasm for that, so I'll just leave it there.
Yeah, because
I'm
like
fine
this,
with that.
so this is technically the short arrow from the paper, right?
Yeah, so what is this one?
This is just a plain double implication.
Oh, okay.
If and only if.
Yes. If and only if this one is
Type isomorphism.
yeah.
And then we go to
Then we get
extensional
extensional
type
isomorphism. Yeah. Extensional isomorphism.
yeah. Which is obviously we replace the E. It's just TSO with an E instead of an I. Yeah.
It's like Tesco.
Yeah.
So this is for all x. P of
Yeah. So the W is some word.
yeah. So maybe I should have picked W here, but so here we just have A and B. So these are our P and they have to be Langs now, right?
Well, they don't have to be Langs. They have to be something that goes from one thing to another. We could define this in Lang and be specific, but it doesn't look like it needs. It
No,
looks like
so
it
it's
can be
just
defined very generally.
they're just P and Q are just functions from both functions from A to B.
No, like I wouldn't touch.
What?
Oh,
This is Tesso. No?
Oh, you think so? Go back. No, because
these are functions,
have
right?
to be inversed. Right, so there are functions that both take a W,
Right.
and then they return a function from A to B, and the other one returns a function from B to A. That's what I think.
Okay.
Because they're like
This is a type isomorphism. Yeah, I don't see it.
So on they are on that line, right?
Mm-hmm.
PW. So actually, we can just do a definition. Let's just write the definition, not the structure for this. Like this might be easier. And so if you
But is P not a P and Q not is P not just a function from A to B? And Q is a function from A to B?
PW is a function from A to B, and QW is a function from B to A. So we can write this as a definition, no structure, like delete all of that. Yeah, so we just write def teso takes a W. Which is and a P and a Q.
What's the type? W is an alpha.
They're all just
And a P and Q are what? P and Q are.
Oh. Is something that takes an alpha. I see what's that. Yeah, and returns a type. Well, returns an alpha. It has to. That's okay. I see. But okay, let's just continue down this for a second.
Sure.
Just
Yeah.
for me.
No problem.
And then it returns a TISO.
Yeah, so I need to say that, right? TISO
Yeah, and then
of alpha alpha.
yeah,
How do I construct a TISO?
and then
Intro.
intro, yeah.
I give it.
Then it's a PW as the first param for F, and a QW. So not TISO.
That would have
intro.
to be an A to A.
Well, it's so not TISO intro. Yeah. Okay. Okay. Yes. Okay. I'm back. It's gonna work. Yeah. So back to where we defined P and Q and delete everything else up to
Sure.
as you go back. Yeah. Cool. So just define P, not Q. So it goes from alpha to A to B.
Okay.
And then we have a new parameter Q, which goes from alpha to B to A. Okay, and then we're going to return
TISO.
TISO PW. No, not intro, not intro. Just for now, do this. TISO PW QW. Yeah, and then I think just do instead of a colon, do a colon equal instead of a colon.
Oh, okay.
Yeah. That's it. Okay, supposed to be it. Yeah.
This has to. What's it complaining about? This is a. But this has to be an A. So this is the A would be a to B.
Oh,
It's expected to
TISO
have
has A to B and
type.
B to A. No.
oh, yeah, I see. Mm, okay, can we go back to Agda's TISO?
Yeah. We can have a look at the extensional one as well.
Yeah, just wait. Okay. I think I'm back. So can we go back? And P goes from alpha to A, and Q also goes from alpha to A. What's wrong with this? So,
Yeah.
okay, I guess let's define A as type 1 and alpha is type 0.
Oh, in here.
Yeah, just as a start.
Okay. Type 1. Type. Sorry, I can't remember what you said.
Yeah, that was great.
PW has type A. It's expected to have type. So does this need to be type?
Maybe. And then I think we can remove the definition. Yeah,
Yeah.
those both of those.
Okay.
Does it make sense? Yeah, so that is Teso. Yeah. And then you have to make the W implicit.
Yep.
Yeah. So otherwise we don't have the binary operator.
All right. Let me just see.
Kind of.
The so in here we have the somewhere extensional. Inverses dot tech ext ISO. Is that how we look for it?
Cool. Yeah.
Is it the file name? Or here we go. Yeah.
No, see, it's just a definition there.
So this maybe it's the my geek font is not rendering these, but because this looks pretty thin. Yeah.
It's weird. There's one below as well.
Yeah, so this is the type and this is the definition.
Yeah.
But P and Q are defined up here somewhere. So
oh, they're just predicates.
They're just predicates.
Which is something that goes from A to type.
Yeah.
So yeah,
that's good.
I think it looks
Checks
right.
out.
Yeah. Woo.
Oh, hold on. So we've defined it in terms of this. Let's just go back here. But here is this one. Yeah.
Oh, that's a good question.
Okay.
Yeah, what is
this is right. But the thing is that
it is?
This is the not the same. No, it is because that's what this Merc if and only if, because we're using this one and but it's the Merc.
Oh, I see.
Merc if and only if prime uses this definition, which probably makes all of those things line up with the triple equality. Where we have that twiddly equality 2, that's just like generic, and then when this gets used here, it's fixing with this particular version of the relation, because this setoid is like an equivalence relation.
Yeah.
So
yeah, but the point is in the end, like if you scroll down, to the and now the type it returns, right, is the same, right?
Yeah, exactly.
Go to definition on that, just to.
Yeah. That's what I did just now. So it just goes up to here.
Oh, perfect.
The triple equality setoid. So it's when we looked inside this inverse thing, it's kind of generic on the relation, but because the return type is this, I think it fixes the Yeah,
Nice.
fixes the.
Okay.
Yeah,
that's
because
good.
on here we have this,
Yeah.
which is sort of generic on the relation, but this thing fixes the relation to be this equals setoid, which is, if we go to it, then it no, we go down some rabbit hole of setoids.
I think it's fine.
Yeah. Okay. Good.
Okay, let's
So now hopefully we can rewrite that theorem in terms
yes,
of
but
this.
I think you would need to
Yeah.
reload.
Okay, so I need to remember how to do that.
It's like just
Restart server. There we go.
Hmm.
The only thing I ever run from the command for. Oh yeah, okay, do it.
Yeah. So let's go to the top.
Yep.
And let's just slowly scroll down here. Okay, so that's just a normal, that's normal. Okay, I'm at line 36.
Yeah.
I think
So
that's
now we
the
have this.
first one where I should have used
three line.
No, I think that's
Is
a
it
2
three?
line.
Yes,
Because-
you're right. Sorry, this is the Merc.
Yeah,
If and only if prime.
yeah.
So now we need to use. Well, shall we go down and rewrite them as we go, or
Yeah. Oh, yeah, let's do this
instead
one
of
first.
test? This is Tissot intro.
C.
D. Well, these are going to be. I keep having to move your face. I don't
first
know
two
where to
should
put the
be-
faces.
Sorry?
I keep having to move your faces on the screen.
Yeah.
You know, the Zoom thing, but there's no convenient place for you to go. Oh,
I
top
know
left.
exactly what you feel like.
I can move on the other screen. There we go.
Yeah.
People watching this will have no idea what I'm talking about.
Yeah, because you don't see see the faces, you don't know why is this guy just very slowly moving.
Yeah,
his
it's just
mouth
like moving the mouse just
and
randomly
it
around.
stops working. Like I don't understand. Super annoying.
Okay, so we have more cases to do now.
Yeah, basically that's it. Yeah, so should be just intro and exact trifle if we're lucky. See, we're in the Christmas spirit.
Yeah.
This
Oh,
one.
I can't. No. I'm just now. I'm just.
No,
being
I think
stupid.
this
There we
one is
go.
exact P unit. I'm gonna just guess. I didn't even look.
No, sorry. At that stage in the day. No.
No.
Unit.
Okay. I need to look. Okay.
So we need to think now. Let's think. Trifle.
Yeah.
So we've got a REFL, an equality between REFL.
I think it's apply trifle and then trifle. So basically like, oh wait.
No, but we've got an equality between. Oh, hold on a second. It's telling us this has type.
Okay, what
Is it
about
an
this?
equality equal to something?
Yeah.
Yeah, fun, right?
Well, this thing is has type of new epsilon.
That should be rifle, and then rifle equals rifle. So
Can it figure that out? No.
Can't we intro that X somehow.
Yeah, we need to do maybe intro x and then sump at x, or just and then sump at x. Yeah, there we go.
Yeah, and the
And it
type of
should-
x is the same as the one of trifle.
Yeah,
So
it doesn't
ReProving.
seem to.
maybe?
It doesn't need to. It doesn't seem to want to do that.
Well,
uh,
oh, fun. Like we know x is trifle. It just doesn't
Yes.
know it.
It doesn't know it.
Is it destruct? Like cases on x?
Yeah, let's try that.
Cases x on. Cases x with.
Yeah. Then don't know.
I think underscore is fine. Yeah. And then that should be trifle. There we go. Or rifle,
Sorry,
or
exact
trifle. There we go.
Ah. Oh wow.
Yeah, so the only way that can be constructed is with trifle. Ooh, that's nice. There's a thing for this. Can we go to the type.lean?
Yep.
So match pattern. Oh, yeah, no, I think we did everything we could. Can we do attribute sump t rifle? Just or for trifle, yeah.
Yeah. Oops. I can't remember the.
Oh, just an attribute,
Yeah.
like without anything. Sorry.
Yeah. Yeah.
Without anything. Just no
Without
at.
the at.
Yeah. Attribute, and then square paren, sump, and then close the square space, and now trifle. And you can also do copy that line and then try. This is a stretch, but TEQ rifle. Yeah, that doesn't work.
Not a proposition or a definition.
There's something you can do with constructors that have only one constructor that also helps it, but I can't
We have
remember.
this under REFL here as well.
Yeah, but that is rifle. That's
Yeah.
very specific.
Maybe it. Do I need to reload or will it?
You would need to reload for any changes to propagate between files.
Pop, rebuild. Oh. Synth did that.
Maybe if you go up before intro, right?
This one.
Type. Yeah, before that intro x, do a sump.
Hmm.
And then do a intro and subst. Subst underscore vars. What? New line? What? How could you not?
Let's substitute this X, right?
Yeah, okay. RWX?
Oh, hold on. No, it has no, because this is just has type.
Oh, it's a type.
Yeah. Yeah. So it's the as much as it can do. There's not like an equality here or an assignment. Yeah.
I don't want to do cases. I don't.
We'll see what it did. Don't know whether that will help.
Yeah, maybe.
Let's see.
But if we can
No.
only use one constructor, doesn't the constructor tactic maybe do that?
Ooh. Worth a shot. Worth a shot.
What's the suggestion? Oh, constructor.
Just use the
Yeah.
constructor tactic maybe, but just that's just a wild guess.
Yeah. No. Where should I
But
stuff it?
that might be exactly what I thought of. Like,
Mm.
constructor at X. Yeah.
Yeah, we don't have that.
But I think Gregor
We
is
don't
on
have that.
something. I think that's what I was thinking of. Yeah.
Mm.
Well, okay. It's easy to build this tactic that says cases
Yeah.
X. Exact trifle, like, but it's
Exact trifle.
yeah. Okay.
It's gone screwy with the printing here because it thinks it's a comment.
Oh no. Okay, then
The grammar's gone funny.
then we do need
There's a bug.
we do need to use Unicode then. I think it's a good reason.
Let me see if I can well, let me go back to this search I did for extension. Oops. Extend. What? Oh, I'm in the wrong thing. Yeah. Let's go back to the project.
I think it's an ace. Yeah.
Yeah, look, this is it, but it looks funny. And it's rendered as like the real, if I do like describe char, it's going to be like, yeah, long left, right arrow, but it's not very long in my font, is it?
No.
It looks a
Kinda
bit silly.
Almost the same as the other one, which is annoying.
Yeah, this is not good because this is probably like short. Long left, right arrow. This one is left, right, arrow. So I
yeah, I'll find something.
Just my font. Yeah.
I think I'll yeah, I'll do some cleanup and digging here on this. And then the other one was the no confusion. That also needs
Which I think is the most
some help.
poorly named thing because it's. Can you imagine the amount of confusion that it's caused? It has no business calling itself no confusion.
Also, can you imagine the amount of confusion it will still cause me? Like, and
He's
others.
he's just
when I try
mocking
to
us now.
explain.
No confusion here.
Yeah.
No confusion.
Ah.
It's been the most confusing thing so far, definitely.
Yeah. And this video is being sponsored by confused.com.
Yeah.
Where's my money? An elaborate ad to one person. Yeah, okay. Well, this is still very helpful. Like, yeah, we uncovered a lot of things that I need to do to make it possible for us to do simple proofs.
Well, it would be nice. So, like one of the sub goals of this was to see how nice we could make the lean proofs.
Yeah.
I suppose it's a matter of taste, whether you think this is nicer than the tactics. But it'd be nice to see if something like this was possible for the the falsy ones.
Yeah, I think there's potential, but yeah. Hey, if this was in prop, it would be different. It would have been a lot easier. But I have to say I'm quite impressed with Agda's way to figure out the no confusion thing.
Yes.
I wouldn't say it makes a readable proof in the end. Like, I'm not gonna compliment it there. It might be too short. But then the lean is like way too long. And it almost makes it looks impossible to not use tactics.
Yeah.
Which is also not cool. So
Well, I mean, the
I
thing
would
is,
give both languages a mark down here, but
yes,
Agda is winning. Agda's not losing as many points. It's very few points.
Yeah, one thing I
Definitely
will
in
say
terms
though
of
is that
elegance, it has win so far.
Sorry.
Yeah.
I said definitely in terms of elegance, it wins so far.
For the contradiction case, yes.
Yes.
Yeah. But yeah,
I mean, because perhaps there's a different way of expressing it than this. I mean, this is just what the tactics came up with. Perhaps there's some better way of expressing it.
Yeah, just out since this is like the last 5 minutes or something, like just out of interest, can we do the same theorem as T?
Yeah.
But just in prop and then print it.
Good call.
Because that was going to be the first thing I was going to do.
Yeah. How many
just do a
times do I
plain
need?
equality and then print it.
Print it.
So yeah. See, this
is okay. So yeah, if we had similar,
this is still long
stuff. Yeah, but the thing is that this absurd is more like what Agda is doing, because this absurd is expressing the fact that such a case can't exist, something like that. So if we had similar facilities for our equality,
yes.
like if
now
I check this,
can we go to tdecidable.lean and see if we have an absurd function? Yeah.
T-decidable. Yeah.
Great name. There's Tadsurd.
Oh, Tabsurd.
Tabsurd. Yeah. So so this should be helpful.
Yeah, we should be able to define something like this.
No, I think this is exactly absurd.
Yeah.
Oh yeah.
Yes.
Can we copy that proof for theorem T prime prime? Yeah. Yeah. Now T prime 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 and the triple equal again.
Yeah, let's try that.
And then
I
tad
want this
surd.
one. We'll do the refine on the tad surd.
Yeah.
Whoops.
Basically, I'll copy the proof for T triple prime.
Oh yeah.
And yeah, remove the by, make it tad surd, import.
What's it called? Tabsurd, yes.
Just
Tabsurd.
Yeah. Of. Yeah, you have to
Decide.
search that one.
Well, let me go there.
And we have to
Not P.
find that in T decidable.
Ah,
But it will have a. It's of T decide.
of T decide. Okay. Nice.
No, the other one.
Oh, apologies.
No.
Of
It's
T decide, and then
T
TEQ,
rifle and T
and
decide.
then T decide.
And we just have to import T decidable.
Good. I need to say open. Oh, it's not
I
happy.
think that should be good enough. I think you just need to. You might need to say ktd.std. And then reload.
Don't see any errors. This is good. T decidable one. Hold on. I need to say
It's good.
this. No.
Okay.
You also need the triple equality in the theorem.
This one?
Yeah.
Yeah.
I think so.
It is there?
Oh, is
This
it
one
there? Sorry,
So
It's quite small, so
yeah.
Yeah.
Oh, okay, I see it now.
So how does it synthesize these? This is the constraint, right? So it needs a T decidable of P, so that we need to define instances.
Yeah, there's a large chance I made a mistake here.
Yeah, but we need here we are, decide instance of decidable eq. So we need instance of T decidable for something. Yeah, I'm not sure how this works.
Where's the one for eq? That's interesting.
Yeah.
Yeah, but that is for
Binary, Boolean eq. So we need one for instance to T decidable. Well, it's T decidable eq. We need to apply this function. We need instance of T decidable for prop equality. Which one are we actually using? Of T decide eq false. So this one. So it's trying to find an instance of T decidable for
maybe do open, maybe also do open, like
yeah, maybe it's not bringing in the instances. We'll just see. Yeah, 1 equals. So we need it's looking for an instance of T decidable for TEQ, which presumably it should have. Oh, I know. Sorry, thinking of Jubix. Do I say T decidable, or do I need the whole thing?
Nice. I think that's it. Okay. Now at least we've tried. Okay.
Yeah. So T decidable for TEQ TEQ AB looks like it's missing. Because what instances of T decidable actually are defined here?
Yeah. For bool.
Yeah, but this is T decidable eq, not T decidable.
No, one above it is 79.
That's also T decidable eq.
Oh,
Different. Isn't that a different type class?
yeah. Sorry, my bad.
Yeah,
you're right.
But maybe that's some. Oh, hold on a second. It's just an abbreviation. Okay, so. All right.
Okay.
What does abrev mean? Is it a type synonym? Is it a synonym or? Oops.
I couldn't figure out the difference between abrev and diff. But like in this case, I don't think you can do this with diff. So I think abbreviation can do more.
Okay, so are we just missing the instance? So we got instant T decidable eq for bool. Are we just missing one for T decidable eq of TEQ? Ah. No, here it is.
But A and B are
bool. We want A and B to be what?
So let's just go back.
These are nats, right?
What if
maybe we just need that?
Can you turn them into bools just for?
Yeah, let's just say it's true. It's false.
Yeah.
So now it has the wrong type.
Okay, that's
better.
Yeah.
Function expected to tech tq.refl. Yeah, this is constructor T decide. Okay, we go here. T decide. There it is. Take me there. No. No, that's not what I want. Is T decide defined here? Is this where it's defined?
Yeah.
So it's a what? Something to bool. Yeah, okay. But this refles. Oh, what? So eq.refl. So this decide also returns a bool, right? Well, what is this big? What does it mean to call eq.refl? So it returns.
Yeah, you pass in a type and it gives you two of the same.
So its problem is that
you go to teak.refl just check.
Oh.
Yeah, there's the mistake.
Okay, so the whole definition is a bit wrong. Interesting.
Yeah, let's move that X.
But it's going to break everything else?
Oh,
probably.
Yeah. Oh, okay. Let's just go back to
Sure.
the actual geek.refl, just to double check.
So it's literally 2 type parameters to prop with the actual.
Okay.
And then REFL here, the RFL is the function which has the implicit. Where our constructor is basically has an implicit.
Yeah.
So maybe we should have it more like this.
Yes.
No doubt there was a reason why we didn't. But
yeah, go back. To type a thing. You'll see I have the match pattern, but it makes no sense to have it like Jan was.
No, because it already has it implicit.
Yeah, but like now we know why we needed it.
Yeah.
Our original definition was wrong. Like
Interesting.
So yeah, quickly fix it. Just I know it's
well,
gonna break.
I'm worried we'll break everything, but at least we can. So we have this one.
Yeah, you can make a pull request that is broken, and I'll go fix it.
I can't do that. It's against my ethics.
No, just make a branch.
No.
A broken branch. Like this is too much work. Like, I'm happy.
No, I'm joking here. Right.
Okay.
So we're still a bit wrong.
Yeah. We need
everything. No.
You need didn't you have you have to change the X to A, right?
Need to
Or the A to X.
Yeah.
Yeah.
And then we need another alpha line 12. Alpha to type U.
Oh yeah.
So there we go.
And then then we use the
and that should be line 20 should be TEQ REFL 1.
Yeah, exactly.
Yeah. And the rest should work.
Yes. Because we're actually passing this by we're passing the implicits here.
Yeah.
Using the at.
Yeah.
Okay, so what does this mean now? I forget why we were even doing that. Oh, because we want to be able to pass in the bool here. No, I need to reload, right?
Yeah.
Yes. This has a chance of working if it wasn't for everything else breaking.
Yeah. But we might be lucky.
Yeah, because we were.
We're very lucky.
Wow. Okay.
Now, does it work for NAT?
Yeah, good question. Okay, I'm going to keep this because I want more primes.
The ultimate.
1 is not equal to 2.
Oh.
Boo.
Okay. So I
because
just think
no. We just need the instance for NAT.
Yes.
That's all we need.
Yeah, it's pretty easy.
Well, I'm not sure how easy it is, but
yeah, but yeah, that's something I can work on.
So
yeah, that's BEQ. No, you want the. Well, I guess I don't know.
This one, we want an instance for T decidable eq of NAT, right?
Yeah.
And then presumably, well, you've defined it here, so we need decidable type decidable equality for. You need another one of these for NAT.
Yeah.
But what do we actually care about? We care about we care about int or something. Well, we're only doing this for a demo, but we need not only NAT, but we need chars or something. We're going to do. But chars are just NATs, aren't they? Because when it prints out here, it says.
Yeah, we might need this for type as well, which is not true. So. But yeah, this is kind of the thing. I think this is the direction, right? It's like,
Yeah.
okay, what would prop do, and then make type do the same thing prop would do.
Yeah.
This is how we fix lean to work with types as well.
Mm.
Yeah. This is the good thing is every frustration here that we have is the thing that will make the paper interesting.
Yeah.
If this was all trivial, then it would be the most boring paper. So then there would be no point in writing it. So
Yeah.
so yeah, this is all good news, these frustrations.
Yes.
Unfortunately, these are quite boring frustrations, but
Well, it's annoying that we need to do this in Lean. I'm surprised no one's told us, because I saw the Zulip thing that you posted, and no one said, "Hey, you shouldn't be doing that. You should be doing this," which was I was sad about, because I was hoping someone was going to say, "Oh, you import this thing, and we got all this ready to go." But no, it was like, "No, you need to define that."
yeah, yeah, it was unfortunate. They provided some good advice, and then I had to go back on it as well because it didn't. It worked for a while, but then when you start using it more, it doesn't work. So, but yeah, they're still very responsive and helpful. So
yeah.
I think like there's more follow-up questions here, but in the end, we are in uncharted territory. But so yeah. All right, so that's a good place to stop the stream with uncharted
Yes.
territory a bit. So yeah, see everyone next time.
Next year.
Yeah, next year. Yeah, yeah. So we'll discuss it. They don't go anywhere, but like I'm gonna stop the stream.
Okay.
Bye bye.